I'm presenting our paper, Test Time Scaling Improves Selective Question Answering. The conventional language model lifecycle involves computationally expensive pre-training, followed by less expensive post-training to improve usability, and then relatively minuscule compute expenditures per user request, typically consisting of a handful of neural forward passes. In fall 2024, OpenAI announced that by investing dramatically more compute at inference time, their language models could solve reasoning problems which previous state-of-the-art models could not. Among these were hard math and science problems. They also showed this exciting compute performance trajectory, where allocating additional inference time compute allows the model to solve a higher proportion of these problems. However, this exciting line of research has not yet shown whether these models can use test time compute to help them discern whether their most likely answer is correct or not. We set out to answer this question. I'll start by defining a few terms. Test time compute can be scaled in several ways. In our experiments, we prompt specialized language models to generate long chains of thought before producing their answers. We measure this computation in tokens. Budget forcing is a method introduced by the S1 team, which controls the compute allocated to each problem by truncating excessively long chains and appending weight to insufficiently long chains. A model's confidence in its answer refers to the likelihood it assigns that answer, conditioned on the question and the chain of thought it's generated. A selection function is an indicator function which determines whether a system will answer a question or abstain. These are commonly used in settings which have non-zero risk associated with delivering an incorrect answer. For each reasoning-intensive question in a dataset, we ask a specialized reasoning model like DeepSeek R1 to generate a chain of thoughts. Along the way, we force it to answer using truncated chains. After a short while thinking, it will produce an answer, although it might have low confidence in this answer. As it thinks for longer, this answer might change. It might even change a few times. Its confidence could vary as well. What we're interested in is whether, once it's landed on a correct answer, can it use additional inference time compute to increase its confidence in this answer and distinguish it from its previous incorrect answers. We test this by plotting the confidence that these models have in individual answers to AMY problems as they invest increasing amounts of test time compute in solving each problem. Here, correct answers are indigo and incorrect answers are orange. The 32 billion parameter DeepSeek R1 is remarkably strong in this capacity. Whereas its incorrect answers hover at medium or low confidence with additional compute, once it strikes upon a correct answer, it uses additional reasoning to quickly consolidate its confidence to nearly 100%. On the other hand, S1 is not nearly as effective at using additional reasoning compute to distinguish between its correct and incorrect answers. Its correct answers hover at moderate confidence range, while a handful of its incorrect answers are boosted to high confidence values. This is despite it delivering comparable performance to R1 on the overall accuracy metric. We propose an evaluation setting which highlights these differences. We define utility to be the number of correct answers minus the number of incorrect answers. Where a system abstains, it incurs neither reward nor penalty. When we force either model to answer every single question, they deliver sub-zero performance in this setting. But when we allow them to abstain unless their confidence exceeds 95%, a wide performance gap appears. Still, both models outperform a zero threshold baseline in this setting. We further observe that both of these plots represent slices of a three-dimensional surface. On the left, we show the utility surface for R1. Redder regions indicate more frequent answers, while bluer regions indicate more frequent abstentions. Utility can be improved by increasing either the selection function's confidence threshold or the compute budget. On the right, we see that S1 operates overall less competitively, and generally separates less from the break-even point indicated by the gray horizontal plane. We encourage future test time scaling research to report performance in selective settings like these, which could more effectively address real-world constraints in high-stakes domains. I'd like to thank my collaborators, Jeff and Ben. Please don't hesitate to reach out if you're interested in the effects of test time scaling on confidence calibration and the opportunities that this paradigm creates in selective question answering.